In this video, we will look at the Heisenberg uncertainty principle, and I hope that this video will give you new graphical and mathematical insight into this uncertainty principle. So we'll start off with Louis de Broglie's wavelength, whereby he proposed or postulated in his PhD thesis that particles behave like waves, just as indeed light is dualistic in nature, whereby in some situations it seems to be like a wave and in other situations it seems to be like a particle. He postulated that for electrons and for particles in general, they would also have this wave-particle duality. And he put forward this wavelength lambda for a particle, relating it to h over p, where p is the particle momentum, in other words its mass times its velocity. So we have this reciprocal relationship between the particle wavelength lambda and the momentum of the particle p. And just a quick note to say that he did indeed obtain a Nobel Prize in Physics in 1929 for his discovery of the wave nature of electrons, because what he postulated here was indeed found to be experimentally true by the Davison-Germer electron diffraction experiment, showing electrons to behave like waves. So to motivate our understanding of the Heisenberg uncertainty principle, I want to actually take us back to a simple Bohr model of the atom with a de Broglie wavelength representing an electron in orbit around the nucleus of a hydrogen atom. And so what we have then is this electron now as a wave function, and I'm going to simply use cos kx, where k is the so-called spatial frequency or angular wave number. So I'll quickly unpack that now and say that the angular wave number, or the spatial frequency k, corresponds to the number of wavelengths within some interval of distance 2 pi. So therefore, if we say that we have k wavelengths per interval 2 pi, that means of course that k times the wavelength will give us 2 pi. This diagram here will help you to understand that. If we consider some distance around the circumference of this circular orbit here, if we consider the distance 2 pi, then we could count up how many wavelengths of this wave function actually occur within that distance 2 pi. So we can see here approximately 1, 2, 3, 5 wavelengths are across that interval 2 pi across the circumference of this circular orbit. So just there I want to motivate a very simple understanding of spatial frequency in connection to a wave function. Now, if we go back to what Louis de Broglie had said, with his wavelength being equal to h over p, the momentum of a particle, we can rearrange that and say the momentum of a particle is equal to Planck's constant h divided by the wavelength of the particle. Furthermore, we could just multiply the top and the bottom of that equation by 2 pi, in other words multiplying it by 1, simply to rewrite it in the following form, where the momentum of a particle is equal to a constant h cross or h bar, I'll define that in a moment, a constant multiplied by the spatial frequency of the particle. Now, just to quickly define, h cross or h bar is simply h over 2 pi. In other words, that term there, which allows us then to use k, which is the 2 pi over lambda, for the spatial frequency. And therefore, we can say the momentum of a particle, p, is equal to a constant times the spatial frequency of the wave function. So how then does that relate to Heisenberg's uncertainty principle? Well, we can see that the uncertainty in momentum of a particle multiplied by the uncertainty in the position of a particle, according to this principle, must always be greater than or equal to some constant, in this case h cross over 2. So what do we mean by uncertainty? Well, here I want to talk about really the level of precision that we have in that particular measurement of a particle. So for example, delta p would be how precise we can be about the particle's momentum, its mass times its velocity, and delta x would be how precise we can be about where that particle is. So to help understand this a bit more, consider it in this very simple form here, where we've got some value A multiplied by some value B needing to be greater than or equal to some constant, because that's exactly what this principle is saying. So visualize it in this way. If we've got some value A represented by the height of this bar here, some value B given by the height of that bar there, we're saying that A times B must always be greater than or equal to some constant value. So I'm choosing here to represent the constant value by that dashed line across this bar chart. So what does it mean then if we require A times B to be greater than or equal to some constant value? Well, it means, first of all, think about this, we could increase A, and that is fine. If we increase A, we would correspondingly increase the overall product A times B would be above that dashed line, so that's not a problem. Likewise, we could increase the value of B as well, and then A times B would still be larger, at least greater than or equal to the value depicted by that dashed line. However, what this constraint actually means is that if we were to try and decrease the value of A, so in other words, this small value here, if we wanted to make that lower, then we'd be obligated to significantly increase the value of B in order for the product A times B to still be at least equal to that constant value. And likewise, if I were to try and decrease B, then I'd have to correspondingly increase A such that A times B is at least equal to the value depicted by that dashed line. So to again really make that clearer, let's contrast that with the following case. What if we simply said A times B needed to be greater than or equal to 0, where we're dealing with positive values of A and B? Well, it would be no problem at all. We could increase or decrease the value of A, and as long as it's positive, we've definitely got no problem. No matter how large or how small we make A, we can be confident that we will have A times B being greater than or equal to 0. We could increase A to infinity, or we could decrease it to 0. We would always fulfill that requirement. Likewise for B, we could increase it to infinity, decrease it to 0. It doesn't matter, A times B would still be greater than or equal to 0. But that's not at all the case with this central expression here, because if you decrease A, then you've got to increase B and vice versa. So connecting that back to this uncertainty principle, it means that if we want to decrease our uncertainty in momentum, the velocity of a particle, knowing the velocity of a particle, then we've got to correspondingly increase our uncertainty in the particle's position, and vice versa. If we want to reduce our uncertainty, in other words, increase our precision in saying where a particle is, then we've got to correspondingly increase our uncertainty, our lack of knowledge about the particle's momentum. In other words, to decrease our precision about the particle's momentum. So I hope these bar charts have made that clearer, but I want to take this a step further now by giving another demonstration of this principle. So first of all then, here's a very simple way of looking at it. We can again relate the fact that the particle's momentum is proportional to the spatial frequency of the particle. And so here I'm showing 4 different waveforms representing 4 different particles with 4 different values of momentum, because there's 4 different spatial frequencies. This one is a lower spatial frequency. In other words, there are fewer waveforms per unit interval or per 2 pi interval. And as we go down here, we've got more waveforms per 2 pi interval. So k is large here, k is small there. Okay, so if we look at that uncertainty relationship, what does that depict here? Well, imagine if we were to look at some window in space, in other words, have some broad coverage of consideration in the x direction here. In other words, when we've got this broad spatial location where delta x is relatively large, we can see here very simplistically that it's quite easy to spot the difference between these frequencies. In other words, it's quite easy to distinguish different momenta. Therefore, our uncertainty on a particle's momentum, if we're not very spatially localized, our uncertainty in the momentum is quite low. In other words, we're able to say with quite high confidence what a particle's momentum is. Now, what happens if we narrow that a bit further? So now we've got a smaller delta x here. In other words, a higher precision on saying where the particle's position is. What does that now mean? Well, we can see that actually it's a little bit more tricky now. Look at the first and the second case here. It's a bit more tricky now to be sure about the particle's spatial frequency. In other words, its momentum. And so that's what I'm saying here. If we've narrowed the spatial precision, in other words, if we've been more precise, more knowledgeable about a particle's position, it's now much harder to be able to discern what the particle's spatial frequency is. In other words, we don't really know so much about the particle's momentum. And if we keep going with that concept to a very, very narrow spatial localization, in other words, where we've got a lot of confidence about where the particle is, now it's nearly impossible, if you look at these waveforms here, if you were to just look at the region within the blue band, it's very, very difficult to know what the particle's frequency would be, what its spatial frequency or therefore momentum is. And so therefore, as it turns out, we can see we would actually need wider and wider spatial windows to be more and more confident about what a particle's spatial frequency is or what its momentum actually is. And in fact, one could say if you converted this to the time-based case, you'd actually need infinitely long duration of time to really know with absolute precision what the frequency of a waveform is. Okay, so here then, with a very narrow localization, a very small delta x, we're hardly able to distinguish between the frequencies, and therefore our delta p is actually very large. Our uncertainty in momentum is very large. So let me illustrate this now with a graphical demonstration. So here I'm showing simply one waveform, one cosine with spatial frequency equal to 1. And what I mean by that is that we've got one cosine waveform, one wavelength fitting from 0 to 2 pi. So here I've got minus 2 pi, minus pi, 0, pi, and 2 pi, just one waveform, k is equal to 1, fitting within the interval, the distance of 2 pi. Now, what I'm going to do is progressively sum together cosine functions. First of all, then, I'm going to start off with cos of the 0 frequency. Cos of 0 is 1, so I've got a value of 1 all the way from minus 2 pi to plus 2 pi, and in fact from minus infinity to plus infinity. Now, just as with the previous example where I just showed cos kx, where k is equal to 1, where we just had one single waveform, that corresponded to precise knowledge of the particle's spatial frequency, therefore precise knowledge of the particle's momentum. Likewise, in this case, with cos of 0, we have precise knowledge of the particle's momentum. In other words, here the spatial frequency is 0, and so the particle's momentum is 0. And correspondingly, with that precise information, we have absolutely no information at all about where that particle is, because the amplitude of this wave function relates to the probability of finding the particle in any given particular position. And we can see here that we have no knowledge at all. That straight line, that horizontal line, would go from minus infinity to plus infinity, and it would be of uniform amplitude from minus infinity to plus infinity. Therefore, delta x is infinite, but conversely, we've got precise knowledge of the frequency. K is equal to 0, therefore precise knowledge of the frequency, meaning precise knowledge of the particle's momentum, precise knowledge of the particle's velocity. Now here, what I'm going to do to decrease our knowledge of the particle's velocity, particle's momentum, its spatial frequency, to decrease our knowledge of that, what I'm going to be doing is adding together waveforms of different values of the spatial frequency k. At the moment, I've just included just one of them, cos 0x. So this here is the same as that function. I've just got a different y-axis scale here. Now what I'm going to do next is add on another wave function to get a combination of wave functions here. So I'm actually adding together two wave functions. And by adding together two wave functions to get one new overall wave function, what I've got here now is a particle that actually has less information about the momentum because we've added together zero frequency plus the first frequency. And I can keep going with that for, say, adding together another waveform of another spatial frequency, another value of momentum to give this overall new waveform here, this new wave function, which now has 0, 1, and 2. In other words, less clarity, less information, if you like, about the spatial frequency, because now there are three different spatial frequencies, three different values of momentum that have gone into this wave function. So what I can keep doing is adding more and more of the different spatial frequencies, so that by the time I've added together now 7 values, k is equal to 0 all the way up to 6, what we're beginning to see is that we're getting more localization in the wave function, bearing in mind the amplitude of the wave function relates to the probability of finding the particle at any given particular position. Therefore, delta x is becoming smaller as I am increasing the number of momentum values that are going into making up this overall wave function. So I'll keep going further. And now I'm progressively adding more and more cosine functions of increasing spatial frequency. And you can see that by the time of adding 250 of them for this particular choice of sampling, for this simple demonstration here, when I've added together a large number of spatial frequencies, in other words, a large number of different values of momentum, in other words, my momentum now is very uncertain for this particular wave function, look what we see. Suddenly the spatial localization is, for this discrete implementation, effectively a perfect localization of where the particle is. Again, this amplitude is related to the probability of finding the particle at any given position x along this axis here, and now we have perfect localization of the particle. In other words, if we make a measurement, we will know that the particle is there, but that has come at the cost of no information at all about the particle's momentum or the particle's velocity, because we have actually needed to combine all of the spatial frequencies k, in other words, to eliminate all knowledge of the spatial frequency or the momentum in order to get that wave function. So just to finish then, there are in fact a number of these general uncertainty principles. We've looked at momentum and space. It's also true for energy and time, and also in general it's true between the time domain and the frequency domain. In other words, you can look at Fourier transform pairs between different functions and you'll see this unsharpness relationship between them, where if you're sharp in the space domain, then you're less sharp in the spatial frequency domain, and vice versa. Hope that's been helpful. Thanks for listening.